All right, we're going to label this as I always label the new units, Unit 11, gas laws. Okay, so we are going to start with one of the gas laws. I just want to kind of put a disclaimer out there. I'm going to give credit to the scientists that have been involved with all the gas laws and discovered them, and the ones that are associated with. However, I want to make it very clear that that's not the focus of gas law unit. So my exam, I won't ask you questions like who did this, who discovered this law, who discovered that law. What you're going to need to focus on is the actual formula and utilizing it and understanding it versus who was involved. But I want to make sure I give everyone credit. The first scientist that we are going to investigate is Robert Boyle, and it was around the year 1662. Okay, you can imagine way back then. So what he discovered was that pressure of a certain quantity of gas, let me include this because these are gas laws. So pressure of a certain quantity of gas varies indirectly. Okay, so this is a vocab word I want to focus on, indirectly. I believe in your physics class and math class, you use the words indirect and direct relationships versus there's another way you can say it as inverse, possibly inverse relationship. But I'm going to try to use the same vocabulary as you have for your physics classes and as you have in your math classes. So an indirect relationship with volume, with its volume. So the pressure of a quantity of gas varies indirectly with its volume. That's two variables. So let's underline those variables, pressure and volume, the two variables. We are going to consider that temperature is constant. So if it's at room temperature, it's at room temperature. The fact that temperature is noted in a problem, in an example, for it says at room temperature, pressure and volume discussion happens. Because of a temperature may be noted doesn't mean that it's changed. The important thing that it's held constant. So if there's nothing changing during temperature, the relationship between pressure and volume is indirect. So I'm going to actually draw an image. And remember, Mrs. Sulkson is a chemist and a chem teacher, not an artist. So I'm going to draw a container. And within that container, I'm going to draw like a plunger, like a metal plunger. And that plunger looks like that for my purposes. And it has a little handle. There we go. It's going to do that. So you can imagine that plunger. I can push or I can pull that plunger in that container. So what I've trapped here are gas particles. Let me label that. It's a gas, whatever it may be. So I'm just going to place a couple gas particles. Gas is not constant, so they're not really stationary like that, right? So I'm going to place a little movement. Chemists draw the movement by making little dash marks. 1 or 2 dash marks means a little movement, right? So I'm going to put a little movement to these guys. So I'm going to show you 2 scenarios. In this scenario, I'm going to take this and I'm going to take this handle and I'm going to pull it upward. As I'm pulling it up, the volume here is increasing because imagine this is moving upward. So now I went from this volume to here. So you can notice the volume is increasing. So according to Boyle, if I've a volume and pressure are indirectly relationship, that means I've increased the volume, I'm decreasing the pressure. So let's write that out here. I'm going to draw an arrow. So I'm pulling up. That means your volume is increasing, arrow up, and your pressure is decreasing. Okay, so I'm pulling this up. The volume, imagine this thing, the volume goes up, and then my pressure is decreasing. So not too much movement there, and I'm going to keep that the way I drew those gas molecules, I'll keep it like that. Well, let's draw the other scenario that's possible. Again, I'm going to try to draw the same container. I'm sure you guys are drawing a much nicer job at home. No worries. I'll stick to my chemistry job. There we go. I got my plunger, my handle. Let's kind of make my container open like this. So again, you can imagine I can either pull, I pulled it up here and this moved, or in this case, I'm going to do the opposite. So I'm going to show those molecules. And in this case, I'm going to push down. So as I'm pushing down, I'm decreasing the volume. And if I'm decreasing the volume, I'm increasing the pressure. So I'm going to have a little bit more movement. So with that, I'm going to show a little bit more movement by making those dash marks. So that indicates that there is more movement happening because I'm going to describe what's happening here. Of course, if you're just looking at it without any descriptor, because this is just on paper and I've drawn it, they look identical except for the movement. But here I've described that I'm pulling it up. Here I'm pushing it down. So let's draw that. I'm going to arrow it down. I'm going to say I'm pushing down. So I've decreased my volume, right? I'm taking that plunger. Imagine that plunger, and I'm pushing it down. That means you're increasing as a result. Sorry, that doesn't mean you're, as a result, that's increasing the pressure. So here's a relationship that's indirect. That's our only focus for today, is our indirect relationship. We are going to include and talk about the KMT that we talked about in first semester, which is the kinetic molecular theory, the movement of molecules, in particular in this case, gas particles. So there's the movement of the particles. So as your pressure decreases, your movement is slightly less, but your pressure is increasing, your movement's more. So I can also depict it as a graph, graphically. Probably do this in math class too. But let's make sure I got my whole view here. So I'm going to have my pressure. I'll write that in my y-axis, and let me get the view out a little more. And my x-axis is going to have volume. So if you're in an indirect relationship, you're going to expect your graph to look something like this. Again, with the pressure volume having an indirect relationship. I'm going to just remind you that the third variable is constant. Temperature is constant. Because these variables are what can manipulate gases, and this is the gas laws. Specifically today, we're focusing on these two variables, pressure and volume. We're assuming temperature is constant because I'm stating that. However, what we're going to learn in the next couple of days in class is that what's going to happen is if our variables are changing, like temperature changes and volume changes, what's the relationship between these two? What's the relationship between temperature and pressure? What about all of these? What's the relationship between temperature, pressure, and volume? If all of these variables, none of them are held constant, is my relationship then? That's what the upcoming unit and what you're going to see today in the video and what my upcoming lectures and lessons are going to be about. So today, again, our focus is a pressure-volume inverse relationship. If there's an indirect or inverse relationship, mathematically, you will multiply out. So if you have the pressure, the initial pressure, so the initial pressure before any movement, and initial volume before any movement, and in this case, let's just use this example. I've changed the volume and I pulled it up. So if I've changed the volume, you could calculate, I should have just put P2, V2, but regardless, let's switch that around to make it nice and neat looking for you guys. There we go. If I know the new volume, I can calculate the new pressure. Okay, so this is our ultimate equation to be using. Sorry about this mess here, but I want to make sure that it's consistent. Again, it doesn't make any difference mathematically, but since we have P first, we'll write that first there. So P1V1 is equal to P2V2, your initials, and then your change to. Okay, so you can then calculate. So today, what you're going to be doing is practicing 4 problems with this relationship. I'm going to stop the recording right now.